September 24, 1944, Peleliu airfield. The F4U Corsair touched down on coral dust still stained with blood from that morning's fighting, its Pratt and Whitney R 2800 engine settling into a steady idle that would become as familiar to Marines in the rifle companies as the sound of artillery. The pilot shut down after another mission, the 11th sortie that day for this particular aircraft, Bureau number 17883, built 6 months earlier at Vought's Stratford plant. Ground crew swarmed the fighter, refueling from drums hand-pumped into wing tanks, loading fresh ammunition belts, and checking engine temperature gauges that showed normal operating parameters, despite continuous combat operations in conditions that would have destroyed lesser machines. By nightfall, this same Corsair would fly 3 more missions, delivering rockets and machine gun fire against Japanese positions in the Umurbrogol mountains, where Marines were dying in caves that seemed to regenerate enemy defenders faster than they could be killed. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Japanese intelligence officers monitoring American air operations from bunkers in the Philippines and from deteriorating positions across the Central Pacific compiled reports on Marine Corsair squadrons with growing confusion that would evolve into alarm by early 1945. American fighter aircraft were maintaining operational tempos that contradicted every assumption Japanese planners had made about the limitations of air-cooled radial engines and the inevitable degradation of combat aircraft under sustained operations. The mathematics of aerial warfare in the Pacific were being rewritten not through superior pilot training or innovative tactics, but through automotive engineering excellence that allowed American fighters to fly mission after mission, day after day, while Japanese aircraft sat grounded awaiting parts, repairs, or engine replacements that would never arrive. Reliability would prove as decisive as any engagement between pilots, determining which air force could maintain offensive pressure and which would watch helplessly as their operational capability degraded toward zero. Marine Fighting Squadron 121, VMF 121, began Corsair operations at Guadalcanal in February 1943, with aircraft that had already logged hundreds of flight hours during initial carrier qualification trials the Navy had rejected as too difficult. These were not new machines, straight from factories, but veterans of testing programs that had revealed the Corsair's problematic landing characteristics and relegated it to shore-based Marine squadrons, while the Navy equipped its carriers with Grumman F Hellcats. What Navy planners viewed as a rejection, Marine aviators embraced as an opportunity to acquire the most powerful single-seat fighter in American service. The Corsair carried 6 50-caliber machine guns, with ammunition capacity exceeding 1,500 rounds total, could exceed 400 miles per hour in level flight, and possessed climb rates that allowed it to reach 20,000 feet in 7 minutes. More importantly, for sustained combat operations, the aircraft's engine simply refused to quit working. The Pratt and Whitney R 2800 Double Wasp represented the culmination of decades of American radial engine development, a lineage extending back to the Wright whirlwind that powered Lindbergh across the Atlantic and forward through progressive refinements that prioritized reliability over theoretical performance peaks. The engine displaced 2,800 cubic inches across 18 cylinders, arranged in 2 rows, producing 2,000 horsepower from a power plant that weighed just 2,300 pounds. Design engineers at Pratt and Whitney had specified tolerances that allowed engines to function properly despite combat damage, tropical heat, salt air corrosion, and maintenance performed by mechanics working from drum-topped workbenches rather than factory floors. Every component reflected design philosophy that assumed engines would operate under adverse conditions, far from specialized repair facilities, maintained by personnel with basic training rather than factory-level expertise. The cylinder barrels featured deep cooling fins cast as integral parts of the cylinder structure rather than added afterward, providing exceptional heat dissipation that prevented the overheating problems that plagued tighter tolerance engines. The valve train used pushrods and rocker arms in arrangements that allowed adjustment with simple hand tools, eliminating the need for specialized equipment or precise measurement instruments. The ignition system incorporated dual magnetos, providing redundancy that kept engines running even after combat damage destroyed half the electrical system. Most critically, the engine tolerated extended operation at high power settings without the rapid degradation that forced Japanese engines to be derated or replaced after relatively few flight hours. An R-2800 in regular service could log 500 to 700 hours between major overhauls under combat conditions, and examples properly maintained exceeded 1,000 hours before requiring factory-level work. Japanese engines designed to similar performance specifications rarely achieved half that operational lifespan, and late-war versions built with inferior materials and by undertrained workers frequently failed within 50 to 100 hours of operation. The Nakajima Homare 18-cylinder radial that powered the Kyoshimji Shont Ttere Hayate fighter, considered Japan's best late-war design, exemplified the reliability gap that would determine aerial superiority in the final years of the Pacific War. On paper, the Homare's specifications appeared impressive. 35.8 litres displacement, 18 cylinders, designed output of 1900 horsepower at takeoff power. In practice, the engine proved extraordinarily difficult to manufacture and maintain, requiring precision machining and careful assembly that Japanese industry could not consistently provide as the war progressed and skilled workers became scarce. The Homare's tight tolerances intended to maximize power output made the engine sensitive to variations in fuel quality, manufacturing precision, and maintenance procedures. Japanese 92-octane fuel lacked the anti-knock properties of American 100-octane or 130-octane fuels, forcing Japanese engines to operate at lower compression ratios and reduced power settings to avoid detonation that would destroy pistons and cylinder heads. This fundamental fuel quality difference meant Japanese engines could never reliably achieve their designed power ratings, even when brand new and properly maintained. As American submarine campaigns strangled Japanese oil imports and refining capacity degraded, fuel quality deteriorated further. By late 1944, Japanese aviation gasoline frequently contained impurities and had octane ratings below specification, causing engines to detonate, overheat, and fail at accelerating rates. The Homare required meticulous cylinder head installation, with dozens of thin steel plates that had to be removed from hot molds within precise time windows during manufacturing. By 1945, most factory workers were teenage volunteers or conscripted labor with minimal training, making consistent quality control impossible. Engines left the factories with improper clearances, inadequate lubrication, and assembly errors that guaranteed rapid failure under combat stress. Field maintenance compounded reliability problems. Japanese maintenance doctrine assumed relatively static operations from established air bases, with dedicated engine shops, trained mechanics, and ready access to spare parts. The reality of Pacific War operations violated every assumption. Japanese forces retreated continuously after mid-1943, abandoning airfields and equipment, operating from hastily prepared strips carved from jungle or coral, and conducting maintenance with improvised tools and vanishing spare parts. Air units lacked proper engine hoists for removal and installation, forcing mechanics to manhandle power plants using ropes and manpower rather than specialized equipment. Major repairs that should have been performed at rear area depots were attempted in the field by mechanics who lacked proper training, tools, or replacement components. Engines were run beyond their operational limits because no replacements existed, accelerating wear and causing catastrophic failures at increasing rates. Japanese naval aviation faced similar maintenance crises despite theoretically better logistics support than Army units. The Mitsubishi Kasei 14-cylinder radial, used in numerous Navy bombers and fighters, required careful attention to valve timing, ignition sequencing, and cooling system maintenance. Field conditions rarely allowed the necessary care, and worn engines lost power, overheated, and eventually seized. Periodic inspections and scheduled overhauls that maintenance manuals specified simply didn't occur, as units moved constantly, fought continuously, and lacked the personnel and facilities for proper service intervals. Aircraft were abandoned during retreats that could have been repaired if proper maintenance infrastructure existed at rear areas. But the infrastructure had never been built because Japanese planning had assumed short, victorious campaigns rather than sustained attritional warfare. The contrast with American maintenance practices could not have been more stark. Marine air groups operating Corsairs from island airstrips maintained standardized procedures derived from pre-war naval aviation practices and continuously refined based on combat experience. Each squadron included dedicated maintenance sections with trained mechanics, specialized tools, and access to well-stocked supply chains that delivered parts, engines, and equipment with remarkable consistency, despite operating thousands of miles from American factories. Marine mechanics servicing Corsairs at Peleliu in September 1944 worked from organizational equipment that included proper engine stands, maintenance platforms, and specialized tools for every required operation. When an engine needed replacement, ground crew could swap power plants in less than 8 hours using standard procedures and readily available hoists, dollies, and fixtures. The replacement engine arrived in a protective shipping container with preservation materials, installation instructions, and accompanying paperwork that documented factory testing, operating hours, and service history. Compare this to Japanese mechanics at Philippine airfields in the same period, jury-rigging repairs with improvised tools, cannibalizing parts from damaged aircraft, and attempting to service engines without proper lubricants, coolants, or replacement components. VMF 214, the famous Black Sheep Squadron commanded by Major Gregory Pappy Boyington, demonstrated the operational advantages that reliable aircraft provided during their deployment to the Russell Islands from September through December 1943. The squadron arrived with 27 Corsairs and immediately began flying combat missions against Japanese positions at Rabaul, the heavily defended enemy stronghold on New Britain that harboured over 90,000 troops and hundreds of aircraft. Boyington's pilots flew daily missions exceeding 400 miles round trip, engaged Japanese fighters in sustained combat, and returned to base where maintenance crews serviced aircraft, repaired battle damage, and prepared machines for the next day's operations. Over 4 months of continuous combat, Black Sheep pilots flew over 400 sorties, claimed 94 enemy aircraft destroyed, and lost only 6 Corsairs to enemy action. Mechanical failures causing mission aborts or aircraft losses were nearly non-existent. The squadron's maintenance chief kept 22 to 25 Corsairs operationally ready every day despite continuous combat operations. Tropical climate conditions that corroded metal and degraded rubber components, and inevitable wear from sustained high-power operations. This operational readiness rate of approximately 85 to 90% under continuous combat conditions exceeded anything Japanese air units achieved even during the war's opening months, when their logistics remained intact. Japanese fighter units opposing Marine Corsairs at Rabaul during the same period struggled to maintain operational readiness above 50%, even before combat losses reduced available aircraft. The Nakaima Ki-43 Hayabusa fighters and Mitsubishi A-60 fighters that defended Rabaul required constant engine attention, frequent replacement of worn components, and careful operation to avoid mechanical failures that would leave pilots deadstick over hostile territory or enemy-controlled waters. Japanese pilots learned to nurse failing engines back to base, reducing power to prevent overheating, adjusting mixture controls to prevent detonation, and praying their machine would continue running long enough to reach friendly territory. American pilots rarely faced such concerns. Corsair engines that took battle damage frequently brought pilots home, despite significant mechanical trauma, and engines operated at combat power settings for extended periods without the rapid degradation Japanese power plants suffered. The campaign for Peleliu from September 15 through November 27, 1944, demonstrated how aircraft reliability determined air support effectiveness in sustained island combat. Marine Corsair squadrons operating from the captured airfield began flight operations just 9 days after the initial landings, even while fighting continued in the Umurbrogol ridges where Japanese defenders held fortified positions in caves and bunkers that proved nearly impossible to reduce with conventional tactics. Marine Fighting Squadron 114, VMF 114, flew from Peleliu airfield beginning September 24, providing close air support that proved critical to Marine infantry struggling to eliminate Japanese positions that dominated the battlefield from elevated terrain. The squadron's Corsairs delivered 5-inch high-velocity aircraft rockets, 1,000-pound bombs, and machine gun fire against targets sometimes within 200 yards of friendly positions, requiring exceptional precision and immediate response to requests from forward air controllers. From September 24 through November 27, VMF 114 flew over 1,000 combat sorties from Peleliu's Coral runway, maintaining operational readiness that allowed immediate response to support requests, regardless of weather, time of day, or intensity of previous operations. The squadron's maintenance crews serviced aircraft continuously, turning around machines from combat missions in less than 30 minutes, when tactical situations demanded maximum effort. Aircraft logged mission after mission without mechanical failures, forcing mission aborts, or preventing scheduled operations. When Corsairs sustained battle damage from ground fire, mechanics repaired them quickly using standard procedures and readily available spare parts. The squadron never faced situations where lack of operational aircraft prevented missions from being flown, never experienced engine failures at rates that degraded combat capability, and never watched helplessly as their machines deteriorated from mechanical problems beyond their capacity to repair. Japanese air units attempting to support their garrisons at Peleliu and throughout the Palau Islands faced the opposite situation. By September 1944, Japanese naval aviation had been devastated at the Battle of the Philippine Sea in June, losing 3 fleet carriers and approximately 600 aircraft in a single day's engagement that American pilots called the Great Marianas Turkey Shoot. The surviving Japanese aircraft and pilots withdrew to Philippine bases, where they attempted to reconstitute combat capability while facing fuel shortages, parts shortages, and inexperienced replacement pilots who lacked the training their predecessors had received before the war. Japanese air strength in the Philippines included approximately 400 Army and Navy aircraft in theory, but operational readiness rarely exceeded 30 to 40% due to maintenance problems, fuel shortages, and lack of trained pilots. Missions flown against American positions at Peleliu came from Philippine bases over 500 miles away, requiring extended overwater flights that stressed engines and consumed fuel Japanese logistics could barely provide. Aircraft that reached Peleliu faced Marine Corsairs with better performance, experienced pilots, and overwhelming numerical advantage. Japanese aircraft that survived combat frequently failed to return to base due to mechanical failures or fuel exhaustion, losses that Japanese forces could not replace. The operational tempo disparity determined the campaign's outcome as much as tactical proficiency or strategic planning. Marines at Peleliu received immediate air support whenever needed because Corsair squadrons maintained high operational readiness and could respond within minutes to support requests. Japanese defenders received no air support because Japanese aviation could not maintain forces in the area, could not sustain operations from distant bases, and watched their remaining aircraft deteriorate mechanically until they could no longer fly. The Okinawa campaign from April through June 1945 represented the Pacific War's longest sustained air operation and provided the definitive test of aircraft reliability under maximum operational stress. Marine Corsair squadrons operated from Yontan and Kadena airfields beginning April 3, just 2 days after the initial landings, immediately assuming responsibility for close air support missions that would continue without pause for 82 days until organized Japanese resistance ended. 10 Marine Corsair squadrons eventually operated from Okinawa, flying combat missions against Japanese ground positions, kamikaze attacks, and providing combat air patrol over the massive naval armada supporting the invasion. From April 1 through June 22, Marine Corsairs flew over 16,000 sorties from Okinawa's airfields averaging nearly 200 missions per day throughout the campaign, with peaks exceeding 300 sorties during periods of maximum Japanese air attacks. This operational intensity required every Corsair to fly multiple missions daily, with individual aircraft frequently logging 4 to 6 sorties in 24-hour periods. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Pilots rotated through aircraft as machines returned from missions, were serviced, rearmed, refueled, and immediately relaunched with different pilots. The logistics of maintaining this tempo seemed impossible, yet marine maintenance crews achieved it through standardized procedures, efficient supply chains, and the fundamental reliability of their aircraft. Corsairs at Okinawa operated from airfields under frequent attack from Japanese artillery and kamikaze aircraft, worked on by mechanics who serviced engines while enemy shells landed nearby, and flew in weather conditions that ranged from tropical storms to clear skies within hours. Despite these challenges, Marine squadrons maintained operational readiness, averaging 70 to 80% throughout the campaign, with some squadrons exceeding 90% during critical periods. Ground crews worked 20-hour shifts during peak operations, servicing aircraft by flashlight when darkness fell, conducting engine changes in pouring rain when necessary, and maintaining quality standards that prevented mechanical failures from degrading combat capability. The squadron maintenance chiefs tracked engine hours meticulously, scheduling replacements before power plants reached operational limits, and coordinated with supply officers to ensure replacement engines arrived before needed. The logistics chain supporting marine air operations at Okinawa demonstrated American industrial capacity operating at peak efficiency. Replacement engines arrived aboard cargo ships from depots in Hawaii and the West Coast, having been rebuilt or manufactured in American factories operating around the clock. Each engine came properly preserved, packaged, and documented, ready for immediate installation and service. Compare this to Japanese aviation at Okinawa, where remaining air units operated from airfields in southern Kyushu, flying missions that consumed most of their fuel simply reaching the combat area. Japanese aircraft attempting to attack American ships or support ground forces at Okinawa faced overwhelming American fighter opposition, fled from combats they could not win, and frequently crashed attempting to return to base after suffering battle damage or experiencing mechanical failures. The kamikaze campaign that Japanese forces unleashed against American naval forces at Okinawa represented desperation born from the recognition that conventional air operations had become impossible. Japanese aviation could not maintain the operational readiness, pilot quality, or aircraft numbers necessary to contest American air superiority through normal combat operations. Instead, Japanese planners converted aircraft and pilots into single-use weapons, attacking American ships with explosive-laden planes flown by pilots who had no intention or capability to return. Even kamikaze operations revealed the mechanical reliability gap that had decided the air war. American fighters intercepting kamikaze attacks flew multiple sorties daily, engaged targets repeatedly, and returned to base where they were immediately prepared for the next mission. Japanese kamikaze aircraft frequently suffered mechanical failures before reaching their targets, crashed due to engine problems, or failed to launch because maintenance issues prevented the aircraft from getting airborne. Japanese maintenance personnel at Kyushu airfields struggled to keep aircraft operational long enough for single kamikaze missions. Engines failed during startup or takeoff, oil leaks prevented launches, ignition problems scrubbed missions, and mechanical breakdowns eliminated aircraft before they ever engaged the enemy. This final indignity captured the absolute collapse of Japanese aviation logistics. Their air forces could not even reliably execute one-way suicide missions due to mechanical failures. The statistical evidence documenting American aviation superiority told an unambiguous story about the decisive importance of mechanical reliability. During 1944 and 1945, the U.S. Navy and Marine Corps flew over 64,000 operational sorties in Corsairs, suffering 189 combat losses to enemy aircraft and approximately 1,435 losses to operational accidents over the entire production run. This operational loss rate of less than 3% to enemy action demonstrated not just pilot skill or tactical superiority, but fundamental aircraft reliability that kept machines flying mission after mission. Japanese aviation losses during the same period approached catastrophic levels that destroyed their air forces as effective fighting organizations. Combat losses, mechanical failures, training accidents, and operational attrition eliminated aircraft faster than Japanese factories could produce, replacements, and destroyed pilots faster than training programs could graduate new aviators. By the war's final months, Japanese air strength existed primarily on paper. The remaining aircraft sat grounded for lack of fuel, parts, or qualified pilots. The few missions flown achieved nothing while consuming irreplaceable resources. American aviation operated with near impunity, flying where it wanted, attacking what it chose, and facing opposition so minimal that the primary danger came from weather, navigation errors, or simple mechanical accidents rather than enemy action. The post-war technical evaluation of captured Japanese aircraft by Allied intelligence organizations confirmed what combat experience had demonstrated. American test pilots flying captured Ki-84 Hayate fighters at Clark Field in the Philippines achieved performance matching or exceeding Allied fighters when the Japanese aircraft were properly maintained and supplied with good fuel. With careful attention, the Hayate demonstrated 427 miles per hour top speed, excellent maneuverability, and heavy armament that made it formidable in combat. These results meant nothing for understanding Japanese operational capability because Japanese forces never possessed the fuel quality, maintenance standards, or supply infrastructure necessary to keep their aircraft performing at these levels under field conditions. The test pilots flew aircraft that had been carefully inspected, repaired by American mechanics using proper tools and procedures, and fueled with American gasoline of consistently high quality. They flew machines that Japanese pilots never experienced after the first few months of the war. The Allied Technical Air Intelligence Unit reports noted that captured Japanese aircraft showed signs of increasingly poor manufacturing quality, with late-war examples exhibiting sloppy riveting, improper sealant application, missing components, and assembly errors that should never have passed quality control. Engine inspections revealed inadequate machining tolerances, improper clearances, and signs of poor material quality that explained the reliability problems Japanese forces experienced. One report examining a Nakajima Ki-84 noted that the landing gear struts showed evidence of improper heat treatment, making them prone to collapse on landing. The Homare engine in the same aircraft had cylinder heads that showed signs of overheating and detonation damage after relatively few operating hours. The fuel system contained debris and contaminants that would have caused carburetor blockages and engine failures. Every inspection revealed manufacturing and maintenance problems that Allied forces never encountered in their own aircraft. The fundamental difference between American and Japanese aviation came down to industrial maturity and design, philosophy rooted in decades of experience. American aviation industry had developed through 20 years of civilian airline operations, airmail service, and private aviation that created infrastructure, trained mechanics, and established procedures for maintaining aircraft in commercial service, where reliability determined profitability. Airlines operating Douglas DC-3 transports across American skies before the war demanded engines that would run thousands of hours between overhauls, airframes that could be maintained by local mechanics at small airports, and designs that tolerated the inevitable variations in fuel quality, weather conditions, and operational practices that characterized widespread aviation operations. Pratt and Whitney built engines for this demanding market, where engine failures meant economic losses, cancelled flights, and angry customers rather than simply dead pilots over hostile territory. This commercial aviation experience translated directly into military aircraft design when war came. The Pratt and Whitney R 2800 that powered the Corsair embodied lessons learned, maintaining airline engines across America's vast distances and varying climates. The designs tolerated imperfect maintenance, ran reliably on varying fuel qualities, and operated for extended periods without requiring specialized attention. Japan never developed comparable civilian aviation infrastructure before the war. Japanese airlines were small, primarily government-supported operations that served limited routes with imported aircraft and engines. Japanese mechanics gained training primarily in military service rather than through civilian airline operations. Japanese industry built aircraft for military requirements without the commercial experience that taught American designers, which features determined reliability under sustained field operations. This experience gap manifested in countless design decisions that seemed minor individually but determined reliability collectively. American aircraft used standardized fasteners that could be removed with common tools available at any airfield. Japanese aircraft used specialized fasteners that required specific tools mechanics often lacked. American engines incorporated generous manufacturing tolerances that allowed them to function despite component wear or imperfect assembly. Japanese engines specified tight tolerances that maximized theoretical performance, but made them sensitive to wear, contamination, and assembly variations. American aircraft featured redundant systems providing backup capability when primary systems failed. Japanese aircraft eliminated redundancy to save weight and reduce complexity, making them vulnerable to single-point failures that disabled the entire aircraft. Every choice reflected different priorities. American designers prioritized reliability and maintainability even at the cost of theoretical performance, while Japanese designers pursued maximum performance specifications regardless of reliability implications. The Corsairs' design exemplified American automotive engineering, a philosophy applied to military aviation. The R-2800 engine featured pushrod valve actuation rather than overhead camshafts, sacrificing some high RPM performance for simplicity and reliability. The ignition system used two separate magnetos rather than a single unit, ensuring the engine would continue running if one system failed. The oil system included generous filtration and capacity that allowed engines to tolerate contamination and extended oil change intervals. The airframe used thick aluminum skins rather than lighter thin materials, accepting weight penalties in exchange for damage tolerance that let aircraft survive battle damage and return home. The landing gear was overbuilt, capable of withstanding carrier landings far more violent than normal operations required. Every major component included design margins that exceeded minimum requirements, providing growth potential for future modifications and battlefield reliability that exceeded specifications. Japanese aircraft design pursued performance optimization that looked impressive in specifications but couldn't be maintained under field conditions. The Ki-84 Hayate was designed to use the smallest possible airframe around the most powerful engine Japanese industry could produce, resulting in an aircraft with extraordinary performance potential, but no tolerance for the inevitable degradation of combat operations. When the engine lost power due to fuel quality issues or wear, when the airframe suffered battle damage, when maintenance fell behind schedule, performance collapsed rapidly. The story of Marine Corsair reliability and Japanese aviation decline at Okinawa represented the culmination of industrial warfare waged across thousands of miles of ocean, sustained over 44 months of continuous combat, determined ultimately by each combatant's ability to maintain complex machines under adverse conditions, far from home factories and support infrastructure. Japan entered the war with an aviation industry that could produce excellent aircraft in limited numbers when supported by meticulous maintenance and operated by superbly trained pilots. When those conditions disappeared, when the logistics system collapsed under American submarine blockade, when skilled pilots died faster than training programs could replace them, when industry degraded under strategic bombing and resource shortages, Japanese aviation ceased to exist as an effective fighting force, regardless of pilot courage or tactical skill. America entered the war with aviation industry, built on decades of commercial experience, supported by industrial capacity that dwarfed Japanese production, maintained by supply chains that delivered parts and equipment across global distances with remarkable consistency. American aircraft were designed for the messy reality of sustained combat operations, maintained by mechanics with basic training using standardized procedures, and operated by pilots who trusted their machines to bring them home. The Corsair flying its 11th sortie of the day at Peleliu, the squadron maintaining 85% operational readiness through 82 days of continuous combat at Okinawa, the engine that logged 700 hours between overhauls, while Japanese engines failed at 100 hours. All this evidence demonstrated the same fundamental truth. Wars are won not by the most impressive specifications or the most courageous warriors, but by the industrial systems that can produce, maintain, and sustain complex machines under conditions where everything works against reliability. Japanese intelligence officers who dismissed early Marine Corsair operations as unsustainable, who predicted American aircraft would deteriorate rapidly under sustained combat conditions, and who assumed their own maintenance problems were typical rather than exceptional, made the catastrophic error of judging enemy capabilities by their own standards. They could not conceive of aviation operations maintaining the tempo Marine squadrons achieved, because Japanese forces had never experienced that level of sustained mechanical reliability. By the time Japanese planners recognized their error, understood that American aircraft were fundamentally more reliable than Japanese machines, and realized that the operational readiness gap could not be closed through tactical innovation or strategic genius, it was too late. The aircraft had already been lost, the pilots had already been killed, the logistics system had already collapsed, and Japanese aviation had been relegated to kamikaze attacks as the only remaining option for forces that could no longer contest the skies through conventional operations. The mathematics were simple and brutally clear. An aircraft that flies its mission reliably is infinitely more valuable than an aircraft with superior specifications that sits grounded, awaiting repairs or parts that will never arrive. A squadron that maintains 25 operational aircraft out of 30 authorized is infinitely more effective than a squadron with 10 operational aircraft out of 50 authorized. Reliability wasn't a secondary consideration or a nice-to-have feature. It was the foundation of air power, determining which force could project strength and which would watch helplessly as their combat capability vanished. Marine Corsairs didn't dominate the Pacific skies through superior pilot training alone. Though Marine aviators were superbly prepared for combat, they didn't win through better tactics, though Marine doctrine was sound and effective. They won because their aircraft worked day after day, mission after mission, while Japanese aircraft progressively failed at accelerating rates until Japanese aviation simply ceased to exist as a meaningful force. Mechanical reliability determined who controlled the air, and air superiority determined the war's outcome. The lesson stands clear for any nation contemplating war. Industrial capacity, logistical infrastructure, and design philosophy that prioritizes reliability over impressive specifications matter more than technological sophistication pursued without regard for maintainability. Japan built an air force that looked formidable on paper, flew well when new and properly maintained, but could not be sustained under the grinding reality of prolonged combat. America built an air force designed to function under adverse conditions, maintained by ordinary mechanics using common tools, supplied by logistics chains that spanned oceans, and the result was inevitable from the moment both nations committed to industrial warfare. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.